Good morning. Welcome to the latest webinar by EA Technology. My name is Neil Davis, and with me today is Anna Garcia. And today we're going to be talking about the LV side of business, and we're going to be looking at getting the most out of LV networks and title turning raw data into actionable insights. So today what we're going to be covering, sorry, just get that working. We're going to do a short introduction about LV visibility, why and what we're talking about in that, and then we're really going to concentrate today on case studies. So case study on quality of supply, we're going to talk quite a bit about pre-fault detection, network resilience, short one on some reverse power flow, and then we've got a session at the end for question and answers. If you do have any questions at any time during the presentation, feel free. There's a question box that you can submit your questions onto, and if we can take them during the presentation, we will. And of course, at the end, we've got that question and answer sessions that we can take anything that we can't cover during the presentation. So without further ado, I'm going to hand over to Anna, who will start us off with the LV visibility.
Thanks, Neil. Hey, everybody. Thanks for joining us today. As Neil just mentioned, we will start by briefly talking about what the importance of improving the visibility on the low voltage network. I will also mention briefly the low voltage visibility approach that we use to develop the case studies that we will discuss today. As we know, the low voltage networks were important but not the focus of attention. Now, the low voltage networks are important and are the focus of attention. This is because the home energy mix is changing. The number of houses with rooftop solars, electric vehicles, behind the meter batteries is increasing. The successful integration of these technologies into the low voltage networks will enable us to transition to a clean energy system that is fair and equitable with the consumers, cost-effective, and that we can maintain the reliability and security of the network. To do that, we need to know what is happening in the low voltage networks. We need to know the performance of the low voltage networks with this new technology are attached to it. This is why improving the visibility on the low voltage network is a must. Here we have an overview of the low voltage network approach that we use to develop the case studies we will discuss today. This low voltage visibility approach is located at the low voltage substation. We use sensors to get the volts and amps. We also can use whichever other sensor that may already exist in the substation, such as transport temperature sensors. We then take all this raw data, putting through sophisticated algorithms to create applications. This is the way we collect, process, and action in the data. This approach has given us insights to improve network performance, support investment decisions, and signal requirements to other market participants. So how we put this approach into practice? We do this through what we call actionable insights. It is worth notice here that the way we process and action the data is locally, rather than send a bulk of data to a cloud to then be analyzed and ultimately be actioned. We do all of that locally. These actionable insights we classify them in three main areas. The operate area is all about here and now, what we can do right now based on live data from the network. The case studies we will discuss today are based on this area, all focus on this area. Then we have the anticipate area. These look at modeling and forecasting of energy future scenarios. And then we have the enable area, that this is all about sending signals to third parties so they can improve their processes. For instance, if we have a virtual power plant, so we send them the signal with the real capacity, hosting capacity of the network, so they can decide how best operate the different distributed energy resources that they have. It also looks at giving access to third parties to use the raw data and develop their own algorithms and their own applications. So how this approach looks like in real life. So it looks like this. The approach is made of hardware and a software. The software part is called VisNet Hub, Visibility Network VisNet, that's why the name. And it looks like the photo on the top left with the cover on, and next to it is with the cover off. The software part of it is called LVCAP, Low Voltage Common Application Platform, and it's located right here in the heart of the VisNet Hub, and it's where the sophisticated algorithms and the applications are located too. So it is worth notice here that we have around 4,000 units in the UK. We have some units in South Africa, some units in Singapore, and in here in the bottom one, you can see this unit in a pole manta setup in here in Queensland, Australia. Here we can see the sensors that we use that are Rawayoski coils, and in the right hand top side we can see how the business look like on a map. So now to give you a better context to understand better the case studies, I will give you a brief introduction to our user interface. So our user interface is called Detect. So here you can see where the business are located on a map. You also can see basic filters, drop-down menus where you can decide which area you are more interested to look at. And the bottom you have the main things going on the network. You also have the number of substations being monitored, the number of feeders being monitored. In the right-hand side, we also have the list of the alerts of the events that are happening on the network. On the top, we have the timeline, so we can go backwards or whatever we want to do. So if we look closely to one of the business on red, we can see on more detail what is happening in that substation. We have the overall schematic of that substation. We have the transformer, the bus bars, and the different feeders. This blue heart means that some pre-fault detection is happening in that feeder. So we also can look in more detail within a feeder. So for example, in this one on red, we can see what is happening is in each one of the phases within that feeder. So for example, we can see here a fuse blow event happening in the phase 1 within the feeder. We also can see more detail about this here in these waveforms. And if we go backwards on time, all these graphics get updated automatically. And we can do so many other things on this user interface. I encourage you to go and watch our video in our YouTube channel, or just ask us.
Okay, 1 sec. I'm just going to try. The sound is low. People are saying the sound is low, so I'm going to see if we can change the microphone. Stop settings. Audio. Or change the computer microphone. Try that.
Hopefully it's better now.
Okay.
Okay, so using the approach that I just explained, what we have found. So here is where we start with our case studies. Our first case study is on quality of supply using the power quality application. So in here, we are going to look at how we investigate a consumer complaint. We then track the source of the problem to get it fixed and ultimately to restore the quality of supply. So to set in the scene, We have a vulnerable consumer that cannot leave the house due to an illness. This consumer has been complaining about some dimming light events. However, the electricity companies say we cannot say anything wrong happening on the low voltage networks. However, the consumer keeps complaining and saying that these dimming light events are causing him anxiety and he's getting dizzy. So he said, I will complain to the regulator. So the electricity company says, let's look close to the network and see and try to see what probably is going wrong there. So we have the overview of the network here. We first identify where is the low voltage cable running, where is the high voltage cable running. We then highlight the area of concern, that is where the customer is located. We then look at the substation when the customer is connected to. We have this substation here. It is worth notice that the red cable here underneath this red cable is the low voltage cable. The blue cable connected the consumer to the substation. Then we also look at what other major loss could be there, probably being the source of the problem. So we can easily see this one here, that is the water treatment plant that is connected to the same substation that connects the consumer. So the electricity company decides to rearrange the network in a way that they isolate the area of concern from the possible source of the problem. However, no improvement with dimming of lights, customers still suffering effects. And at that point, the electricity company decided to install power quality monitors at the low voltage substation. It was installed for several days. The results were analyzed and they were compared against statutory standards. However, no standard was breached. Well, the power quality was able to read short-term flickers, however, in an average of 10 minutes. Therefore, any short events lasting less than a few seconds were not detected. At this point, they decide, well, let's install the monitoring equipment in the low voltage substation. So this monitoring equipment has an alarm threshold set up to a 700 amps peak, and they leave it like that for 24 hours. However, no events were detected during that period of time. So they decided to lower the alarm threshold to 300 amps peak. When they decide to do that, we immediately start to get some event waveforms captured. So here in the graphic at the top, you can see that the current is peaking at 400 and it's trying to get back to normal magnitude quite slowly. We can see that this is like a typical behavior of a motor starting. And at the bottom, we can see an histogram that shows us how many events per hour are happening. So for example, in here, we can see that it's up to 11 events per hour. So it makes, at that point, we understand the annoyance of the consumer. So analyzing those waveforms further, we conclude that it's a three-phase issue. In this one, notice that the residential area is being fed by a single phase. So in this way, we can start to discarding some things. And we can also say that it's a part of an automatic process due to the events happening quite periodically. So at this point of time, and we can also see that the waveforms show a typical inrush current associated with the startup of large machines. At this moment, with these characteristics, we get back to the network or a network schematic and have a look again to see if we can identify any loads that fulfill all those characteristics. So we then can see this small pumping station at the top being connected to the same LV cable that connects the consumer with the substation. And this load is actually fulfilling all the characteristics that I just mentioned. So in that point, we contact them. They were very aware that the soft starter of the motor had failed. They have it on their roadmap to get it fixed in a 3 or 4 months time. But as soon as we let them know that consumers getting affected by this, they fix it the next day. So in here, we can see when that fix happening in the histogram in the outage period. And we also can see that after it gets fixed, we still can see the pump starting up at a much lower current, and a current that human eye cannot detect at variation. So at this point, the consumer were extremely happy, and the quality of supply was restored, not dimming lights. You can pass it over to me.
Okay. So we're going to talk in this next section about pre-fault. So pre-fault is something obviously we try and do across the network, particularly on HV. We're trying to find the faults before they fail and fix them. But what we're able to do, or what we're seeing that we're able to do, and we've been trialing, is pre-fault on the low voltage network. Depending on your network, it can be that the actual low voltage cables can have a very significant effect on the SADIs and SAFEs of electricity companies. So what we're trying to do, of course, is find the faults just in time. So what we're looking for in this particular picture here, the cable on the left had been damaged during installation, and it was starting to let moisture in. The result of that moisture getting in there was that we were getting those mini flashovers, so pre-fault arcing within the cable, and that's detected by that 700 amp peak set that Anna talked about in the last session. So we were getting those short bursts of activity going above that alarm threshold of 700 amp peak. But that is detected. The electricity company in this particular case were proactive. They instigated a planned outage. They located the fault provided by VisNet, impedance to fault, which we're going to talk about in the next. And we were able to take that cable out of service, cut and overlay that section without anybody coming off supply. Now, of course, what typically happens on HV networks and LV networks is that we're usually a little bit too late. So the damage on the right-hand side is what we would typically see. So we've got the actual fault, and if we can be, if we're not proactive, we're going to get the SADIs and SAFEs occurring, and we're going to have to go out there in more of an emergency, unplanned manner and take that out. So what we're trying to do, of course, is do the left-hand side rather than more of the left-hand side, less of the right-hand side. And this is another couple of examples where we're seeing intermittent faults. So these cable joints are domestic service joints where the single-phase cable is tapped off the main LV main going to the different properties. In this particular instance, the one on the left-hand side where we've got the big crack, that was actually in service right up until the point it was excavated, so it never 100% catastrophically failed. That particular circuit was having intermittent problems, and it was causing fuses to blow. So what was typically happening is moisture gets into the cable joint, that causes a flashover, causes the fuse to operate. That drives the moisture out, and when the engineer goes to the substation, replaces the fuse, that holds and that stays in there, so it goes straight back in and maintains. Now, due to that, in this particular instance, the company had installed an auto, one of our products called an Alvin, which is auto reclosing type device, so that will look for the fault and then determine whether it's safe to re-energize the network after a fault, so it reduces the amount of outages. What we were getting with the algorithms, though, is an impedance to fault, so that they were able to then start locating where that may be and then proactively going after it. So the bottom one was quite a serious crack in the service joint. The top one was also exhibiting similar things. So these intermittent faults can be very much of a nuisance, cause you an outage, but when you put the fuse back in, it goes back in. So this enables you to go out there and proactively take it off off the network and reduce the amount of interruptions we're getting. Okay. So if we're going to do this sort of approach, first thing we have to stress is you do need good cable records. So cable records, knowing exactly what's in the ground, the cross-sectional areas, are essential to do this in the most accurate way. But if we know that cable types, then we can, the impedance per meter can be calculated both for the, do you want to swap here? And there's some questions coming in, sorry, Anna. So the impedance can be calculated for both phase to single phase to earth, the loop impedance, or multi-phase phase type impedance. And we can calculate the milliohm impedance to events or to faults. And we can do that with a confidence factor of somewhere between 1 and 9, 1 being that we can see that there's a fault has occurred, but we don't know much about it, to 9 where the fault has been detected and we've got very good location information. So if you can get that and you've got the good cable records, then typically you're going to be looking for the cable joints on the record, because that would be more often the failure than the bulk of the cable. You're looking for excavations. Third-party damage obviously is a key factor when it comes into somebody's disturbed the ground, if that causes a problem. If we haven't enough fault amplitude, then we can do things such as using the cable sniffer, which we can see in the picture at the bottom here. This is where if you get any fault on the cable, you will burn some of the insulation. That will cause gases from the cable to be emanate from the fault or the pre-faulted area. So the burning insulation, that gases will be trapped underneath the pavement or the roadwork there. And we can go to the area of concern highlighted by the location, drill a small hole, sniff for those gases, and give us an indication that the fault is occurring in that location. Infrared is another technique that we can use to try and identify that first. So if we're capturing these fault currents, in this particular example here, we've got something that's happening, phase-to-phase fault. We're happening on L1 and L3. So the coincident here, so that's where we're getting the problems. So 2 phases are involved in it. If we know the impedance of the cable on L1, L3, we've got this variable impedance of the arc. But from this, that's the standard way of doing calculations of impedance to fault using those algorithms placed on that on the VisNet unit, can give us the indication of where things may be occurring. So let's look at a couple of case studies of how that was, what that actually looks like. In this particular instance, we've got we had that impedance to fault. If we've got our cable records, so we have our substation where we're feeding here. We've got the contour or the impedance contours on the network. So we can see that this is a branch circuit. And at the top, the maximum impedance is just under 18 milliohms. So we know in this particular instance, if we've got an impedance to fault in the range of 23 to 26 with this high confidence level, then it must be past this branch circuit. And in this particular instance, it must be towards the end of that branch there. So around 125 or so meters up from the substation, so we can proactively go after it. So now let's get on to a couple of other real-life case studies here. In this particular case, the VisNet units, the monitoring equipment was fitted as part of a load management area program in the area. So it's not actually there for pre-fault location. It's all part of the distributed energy and everything else, and seeing what managing that load on the network. But the pre-fault detection app was unloaded as an additional feature, and during the period that it was on, we were able to capture 85 pre-fault events were captured in this particular location. So we can see again in this time that we've got multi-phase events occurring. So L1, L2 and L3, we've got typical pre-fault activity is leading up to that. So we're getting that event being captured when we're going above that 700 amp peak current waveform, often before the point or not at the point where the fuse will go. So there's enough let through current, but not enough let through current to actually operate the fuse. So 85 events on this. The algorithms analyzed all those waveforms from the measured volts and amps, and determine whether it's a single phase, a loop impedance, or a multi-phase fault. In this case, a multi-phase fault. And then it gives us the best impedance to fault value. And once we've gone above this confidence level of around 6, then we're starting to get pretty confident that we can get very close to the source of the fault, and we can maybe proactively go after that. So in this particular case, we have 31.2 milliohms with a confidence level of 6. If we overlay that on the network again, so the network arrangement, we can see here substation 1 is where we're feeding from, and we can see the contours here. At this point it's 18 milliohms, so 26 milliohms. So we're looking at the source of the fault being around this area of the cable. So we actually, the VisNet is indicating the best impedance value about 95 meters up the cable, somewhere in the region 26 to 31 milliohms, so 85 to 95 meters. In this particular instance, the fault actually did, or the cable did eventually fail. And when we were also looking at the actual fault location, that was also saying about 95 meters. So we were getting very good correlation between the pre-fault location and the actual fault location. As it turns out, in practice, we were about, the actual fault was just a short distance further away from that. So 109 meters up there. With that fault, we're able to go up there, we're able to sniff, and we find that. So we're a shot length away, but even the fault impedance to fault location was saying exactly the same as the pre-fault. This next one, so that was obviously something had failed, but what it's really done is proven the pre-fault and the fault calculations are effectively the same. In this particular case, this is where we've been proactive, or the customer has been proactive and taken something out. So the alarm from the VisNet Hub on the pre-fault app has indicated the fault and has been detected. And in this particular case, the impedance to fault is 50 milliohms, and the fault current was about 4.8 kA. So again, with if it's a short period of time, that may not be enough, or wasn't enough to blow the fuse, but is still a decent level of fault current that we can then use using a cable sniffer to identify. So in this instance, a 50 milliohm location gives us 2 potential sources, one on the corner of this road here and another one where we've gone on the branch there. So we have 2 potential locations that we can go to. If we go there within a short period of time after one of the pre-faults has occurred with a 4.8 type, this sort of fault current, we will have burning insulation, and we can go there and we can use something like the cable sniffer to determine that that's the exact location. In this instance, the electrical diagram was marked, the geofield was marked with a fault location, so that we knew that they could reduce the impact in the event of a permanent fault. So they knew if the permanent fault occurred, that where to go and where was the likely source of it in those 2 locations that we showed on the previous slide. And we can also, of course, reconfigure the network, so to reduce the network load stresses and potentially the number of outage that we have. If we go there with something like the cable sniffer, and we can drill that hole, we can find that this was the exact location. So you can see we absolutely got this 100% spot on. The actual fault and the predicted location was here. So you can go sniff for the gases, see that it's occurring there, excavate and take that out before the failure actually occurs. So if we can turn that from reactive to proactive approach, then we're of course going to get quite a lot of benefits here. We're excavating and repairing that prior to the permanent fault. Customers are remaining on supply. That particular instance, we have 15 customers connected into that, so we've got no SAIDIs or SAFEs incurred as a result of a failure of that and taking those 15 customers off. We're repairing that fault in a controlled manner. Everything in a controlled manner is obviously going to be safer. It's going to be generally cheaper. You can plan it. You can do it in reasonable working hours. We're not looking at overtime. We're not looking at middle of the night type thing. So the safety increases on that. Of course, if we get a fault in that pavement and it's an explosive fault and we've got other utilities in that vicinity, then we could have an instant where we're damaging water mains, gas mains, things like that due to the energy release. So we've taken that out by not allowing that to happen. Everybody's getting better supply, so we're mitigating the risk by having the monitoring on there. In that particular instance in the UK, that they were able to then calculate the positive cost benefit of doing this proactively. You of course are, even with proactive, you're going out there and you're digging the ground up, you're replacing the joint or overlaying a section of cable. So the assumed labour and materials, the planned work within working hours using standard labour rates in the UK was about the equivalent of about 4,500 Australian dollars. The worst case scenario, if it was unplanned, would be maybe about 5,200. So maybe you've got about a $700 saving for proactively going after that. But where the real benefit in this particular case is a proactive approach, it means that you're not incurring the SAIDIs and SAFEs. And in the UK, assuming something like a 7.5-hour fault for a repair fault standard time was about $1,650. So the estimated savings in that one instance there is about $2,350. So if we can move towards that, and you've got the monitoring on there for different reasons, the monitoring is in there, you can still use it in a maintenance or an operation phase to have a cost benefit and safety benefit on the networks. Okay. Next one, I'm going to hand back to Anna to talk about network resilience and fuse blow.
Thanks. Thanks, Neil.
Okay.
Hope everybody is listening as well. Please let us know if no. Thank you. Here we are going to talk about a case study on network resilience using the fuse blow application. In this case study, we will look at how we make visible fuse blow events in an interconnected substation. So to set in the scene, we have a substation with high number of blown fuses events happening. Therefore, every time that they have an event happening, they have to send their staff to the substation to get these fuses replaced. It is becoming quite expensive to do. So because this is an interconnected substation, so it doesn't always have visibility because the consumers are still being supplied from the other end. This is a residential area with vulnerable consumers. This is because the people is spending a lot of time at home because the COVID-19 lockdown. So in this point, keeping the network resilient is very important. So the electricity company decided to install the LV monitor at the substation, at the low voltage substation. So as soon as it got installed, we start to detect potential transient faults. We also were able to see that the problem was happening in the feeder 1. So we took a closer look within the feeder 1. So we can see here the phase 1, 2, and 3 within the feeder 1. And we can see here that the current is picking up to 13,000 amp peaks. And this is the reason why the fuses are blowing. We also can see that this is a multi-phase event. So we then further analyze the waveform to have a lot, like an idea of what is how many events of fuses blown we have. So here in this, in this graphic, each one of the peaks represents a fuse blowing event. So here the green is phase 1, the blue is phase 2, the 3 is phase, the pink is phase 3. So for instance, at the beginning of September here, this means that we lost phase 2 and phase 3, the fuses were blown. So the electricity company were able to see this. So they went back and replaced the fuses. However, later that day, the fuses blew again. Meanwhile, the phase 1 keeps in a normal load current. At this point, they knew it. We were able to provide them with the power location, following exactly the same approach that you just explained. However, they decided, because they were short in staff and they have other couple of issues going on, not to go to look at the power location. So things were keeping like normal when we lost two phases in that point. However, here in the middle of October, they went back to the substation, they replaced the fuses. Later that day, they lost the phases again, the fuses blown, and this time the fuse in phase 1 blow again, blow with them. So they knew about this happening. They decided not to take action, and later in October, they went back to the substation, they replaced the fuses. However, later the fuses were blown again, and the same thing happening in November. But at this point, they decide and they say, like, let's look at the power location. So we provide them with the power location. We knew that was close to the substation because of the magnitude of the current, 50,000 amperes. So we knew that was between 20 and 30 meters, following exactly the same approach that Neil just explained. They were able to locate the power location around 28 meters from the substation, and the power was to the tap in for a street light. So in here on the ground, you can see where the repairs were carried out and the power removed. At this point, no more fuses blow events happening. Therefore, they reduce the operational cost, and the reliability of the network was improved. So here, this is more of a case study, is a sneak peek of what we can see in the under the anticipate area. For example, we can have reverse power data. We will expand on this area in a future webinar looking at case studies on this area. So we are able to look at whichever reverse power data is going on the network. For example, here we are looking into more detail within a feeder, and we can see that in phase 2 within that feeder, some reverse power is going on. We get the alarms, and we also get the waveforms. This data has been enabled us to give to the electricity company, the design engineers, the asset managers to understand the real capacity of the network. And this has helped design engineers to support the optimization and new connection requests. And it also helps to identify potential areas where probably is a high uptake of rooftop solar happening. Therefore, could be an awesome place to do some, to install, for example, a community battery. So it is helping to improve the hosting capacity of the network as well. And for the asset managers, it's enabled them to accurately assess health projections. Therefore, it's improving the investment portfolio. It is worth notice that we have 4,000 units in the UK, and a large number of those units are being used as a business as usual, and other units are on trials. So at the end of the day, this is helping us to integrate, enable us to integrate the different new technologies on the low voltage networks. Thank you.
Okay, so we come to the end of most of the slides. Just to summarize on that, the low voltage networks, as we know, I mean, we're looking at them closer and closer today, where we typically didn't in the past. It was more of a fit and forget. And a lot of the reasons that we're looking at them, of course, is the advent of distributed energy resources and capacity and hosting capacity, things like this. However, what I hope we've been able to share today is that if we do get monitoring on that network, we can also use that more in the operational phase of things. So improving our asset performance. Once we do that, once we stop failures, we can get greater reliability, of course, and safety on that. And it can also help in the in knowing whether we need to invest in that network, whether we can have that capacity, whether we can have that amount of electric vehicles connected, solar and things like that. It can also it can reduce costs in the operation phase, and it can also allow us to make the smarter investment decisions. So it's becoming more and more of an important. But the interesting thing is the more that we look on the low voltage network, we now got thousands of these things out there, the more we're learning and the more use cases that we are getting. It is effectively becoming business as usual now, rather than unusual to be monitoring on the low voltage network. So thanks very much for joining us today. If we've got any additional questions, please shoot them through now. We have answered a few as we've gone along. And if we don't have those questions now, then you can always reach out to Anna or myself. We've got the contact details, telephone, email, and LinkedIn profiles there. So anytime you do have any questions, or if you want to look at any of this in any greater detail, look at some live data maybe on the systems, or whichever you want to do, please reach out and we're more than happy to accommodate that. So have we got any further questions coming through? Oh, we have one. Sorry, we have one that's just come through now. So how long does it take to install a VisNet Hub in a SID substation? Is an outage required? So more of a hardware question in this case. The VisNet takes typically about 30 minutes or so, I think. It's less than 30 minutes, and there's no outage. The sensors are split Rogowski coils, so that's easy on there, and we use G clamps or banana plugs to hook onto the bus bar voltage there as well. Okay. And one further question on the apps. Are all the apps pre-installed, or can you add apps into the system, and is it all done remotely? The apps, depending on what has been enabled, may or may not be on there, but you can always download and upload the apps as and when. So once the system's in place, if a new app is developed, so the trials that Anna was alluding to, and where a lot of this work was done in big trials on the UK networks, is that you can start looking at the apps once an app is developed. So as long as you're measuring volts and amps and say temperature or any other sensor, and you think you've got an application for it, you can develop the algorithm, you can upload that remotely onto your fleet of these monitoring devices, and then enable that through into the software. So if you had an idea that you wanted to try and implement, it's quite easy to do that, and there's no going on site and things like that. So it's very flexible in that particular case, and this is almost a starting point. And as things will go forward, additional apps will be produced, and additional apps will put onto the system. Okay. Any other questions? Yeah, just had an indication from the UK. All apps are not pre-installed. Depends what functionality is wanted, but yeah. So they're not pre-installed as default, and it all depends on what is actually required for that particular network. Okay. last chance for some questions. No, in that case, we'll bring the webinar to a close. Thank you very much for attending. Any questions that you do come up in the future, please reach out, and we're happy to, like I say, answer your questions or show you anything in any greater detail. Thank you very much. Stay safe.
Thank you.
Goodbye.